So, let us look at applications of differential total mass balance equation or the continuity equation. The first application is that suppose if you have arrived at some velocity field, meaning you have found out expressions for Vx, Vy, Vz, you can check whether the given velocity components or found out velocity components satisfy the continuity equation. Second, if you know one velocity component, you can find out the other velocity component. As we have seen, the continuity equation puts a restriction on how one velocity component depends on the other, etc. So, if you specify one, let us say 2D, you cannot independently specify other, it is constrained by the mass balance. A third example is that under certain conditions you can use the integral and differential mass balance equation to arrive at the velocity field. Okay, it is a good example there. And fourth one is once again interesting, we make some measurements on velocity components along let us say two directions. An example of measurements of velocity in a ocean surface, we make measurements along x and y direction and find out what is the vertical component of velocity using mass balance or the continuity equation. Okay. That is why it says estimation of velocity component. And finally, of course, an example including the transient term, with that we find out what is the rate of change of density in a cylinder. Okay. That cylinder could be in an engine or in a pump, etc. Okay. And the scope of the whole course is that we will be using almost always only the incompressible form of continuity equation. Okay. Even throughout engineering, chemical engineering course, any engineering course, we will be almost be restricting only to the incompressible form. Mechanical engineers do use the compressible form as well. Okay, the first application is that the geometry is well known to us, it is flow between the two parallel plates. The velocity components of a constant density implies that it is an incompressible flow, constant density flow field are given by, we are given the x component of velocity and that depends on the y direction. The configuration geometry is shown here, the horizontal axis x, the vertical axis is y. So, the velocity in the x direction varies along the y direction, okay. We also call it as lateral direction. So, flows in one direction, in a direction perpendicular to the flow the variation is there, okay. Flow takes place in the x direction, variation is in the y direction, okay. And there is no variation along the direction of flow, Vx depends only on y. Of course, there is no velocity component in the vertical direction, there is no flow in the y direction, of course, there is no flow in the z direction as well. Now, question is such a flow physically possible? Okay. As I told you, let us say we have found out these expressions and to check, we need to check whether it satisfies continuity equation. Okay, let us write down the equation of continuity for incompressible flow. So, there is no density term, rate of change of density with time is also not there, there is no density in the net mass flow term also. You need to check whether this is indeed 0. Vx is non-zero, but dou Vx by dou x is 0 because depends only on y. So, dou Vx by dou x is 0, Vy is 0, Vz is 0, the red color indicates what is 0. Okay. The first, the derivative is 0, not Vx is not 0, the second and third terms the velocity itself is 0. So, which means that the equation of continuity is satisfied. So, you can conclude that the constant density flow describe the velocity components is possible. A flow is possible only if it satisfies the basic conservation of mass at every point in the flow field. Remember, it is a point form of conservation equation, at every point in the flow field mass balance is satisfied, that is the meaning of this. Okay. Let us take the second example. First, let me explain the geometry, two parallel plates as we have always seen, but now the difference is that the plates are porous. So, there is flow in the y direction as well, x direction and then y direction, there is flow in the y direction. Okay. This results in a two dimensional velocity field. What does it mean? There is variation along the x direction, variation along the y direction. Okay. Now, when there were two plates which were non-porous, then the x velocity varied in the y direction only. Now, because there is outflow through this porous wall, x velocity varies along the flow direction also. So, that is why it becomes 2 dimensional, and we can expect that because there is outflow, the velocity will decrease along the direction of flow. Okay. Just to repeat, if the walls were not porous, then the x velocity varies along the y direction only, but now because the walls are porous and water leaves through that, now along the flow direction the velocity decreases. Okay. Let us now read the problem. For laminar flow, what laminar flow we will understand much later, but right now we can understand to be a nicely well behaved flow. Okay. What exactly laminar, or to get some idea we will understand much later. Okay. Between parallel plates the flow is 2 dimensional, we have seen why it is 2 dimensional. If the walls are porous, the walls were not porous, it was 1 dimensional. Okay. A special case solution, meaning under certain conditions you can derive the expression for x component of velocity. Look at the expression, it has 2 terms, h squared minus y squared, that term tells you the variation along the y direction. Now, we have seen that physically the velocity should decrease along the x direction, that is denoted by a minus b x. It has a minus b x term, which means that the velocity decreases along the x direction, where a and b are constants. Now, what is that we are asked to find out? Find a general formula for velocity v y. We are given v x. As I told you, one major use of continuity equation is that we are given one velocity component, we will have to find out the other velocity component, in this case v y. We are also given one condition which says that if v y equal to 0 at y equal to 0. What is that line y equal to 0? The axis, the central line is y equal to 0. What happens? Flow goes in this direction, flow goes in this direction. So, along the axis there is no velocity, that is why v y is 0, something like a dividing line. Flow goes towards the plus h and then goes towards minus h. So, flow division takes place, and so along this line there is no vertical component of velocity, that is why this says if v y equal to 0 at y equal to 0. Okay, now, second part is what is the value of the constant b. We are given a constant b. If v y equal to v w at y equal to plus h, y equal to plus h denotes the top plate, and at that plate if you are given the velocity, let us say the flow through the porous wall is at a certain value given by v w. If that is the case, how do you find out b? Okay, so, let us proceed with this. Start the equation of continuity as usual for incompressible flow, then dou v x by dou x plus dou v y by dou y. Because it is 2 dimensional case, I am not considering the third term. Okay. Now, we want to find out the v y, the y component velocity. So, let us rearrange for dou v y by dou y. So, I retained dou v y by dou y on the left hand side, taken minus dou v x by dou x to the right side. Now, we should differentiate the given expression. So, if we differentiate the first term, you get minus b, and that is where x is present, h squared minus y squared is a constant, it is a partial differentiation with respect to x. So, if you differentiate, this is what you get. So, if you simplify, you get b into h squared minus y squared. Now, we have a partial differential for v y, we have to get v y, which means that we will have to integrate it. Now, it is not usual integration where we are given d v y by d y, but now we have dou v y by dou, it is a partial differentiation, hence the integration is also partial. Let us see what is the implication of that. Okay. V y is equal to, we will integrate this h squared minus y squared, which is h squared y minus y cube by 3 plus, if it were usual integration d v y by d y, we would write a constant of integration c. But now, because it is partial differentiation and we are doing a partial integration, the constant can be a function of x also. To be more generic, we are writing it as c as a function of x. That is what differentiates from a usual integration from this partial integration, where the constant is a function of x, can be a function of x. Okay. Now, just like usually evaluate the constant by based on a condition, boundary condition, in this case also we are given a condition. So, let us use that. So, using the boundary condition meaning that at a particular location you are given the value for the dependent variable. What does the condition say? V y of x. Why do you say V y of x? The V y is 0, the vertical velocity is 0 along the entire center line for any x. For any x V y is 0, that is the meaning of saying V y as a function of x is equal to 0 at y equal to 0. So, if you substitute y equal to 0 here, this term vanishes, okay, and V y is 0, which means that c as a function of x equal to 0. So, constant has just become 0, c as a function of x equal to 0. Okay. So, that is how we evaluate the constant, similar to usual integration, use the boundary condition and evaluate c equal to 0. So, now your expression for the y velocity component becomes V y equal to b into h squared y minus y cube by 3. Okay. So, this tells you the variation of V y as a function of y. Okay. V x, the x velocity component varied along y direction and x direction also. The vertical component of velocity V y varies along only y direction. Okay, look at the dependency, V x depends on x and y, V y depends on y only, and we have a constant b which can be evaluated. Let us proceed to evaluate that. Okay. So, that is the expression for V y. Now, we are given another condition, we are given another boundary condition. Using the boundary condition V y equal to V w at y equal to plus h. Okay. So, let us substitute that. Left hand side I substitute V w for V y, and right hand side I substitute y equal to h, of course plus h, and if you simplify you get b as 3 by 2 V w by h cube. So, we are able to evaluate the constant b such that the velocity is V w at y equal to h. Okay, let us substitute that, completing the expression for V y. We are asked to find out the other velocity component V y. We are also asked to find out the value of b. If you look at the question, it says a general expression for V y. Why is it general? Because b is a constant value, but once you use a second boundary condition, you get a specific value for b, and hence becomes a velocity expression for the specific problem. Okay. Of course, you can simplify and put in this nice form V w by 2 into 3 y by h minus y by h whole cubed. Now, this velocity profile is should satisfy both the boundary conditions. Of course, when you substitute y equal to 0, this becomes 0, and when you substitute y equal to h, what happens? You have 3 and then minus 1 2, that cancels out, resulting in V w. Okay. That is how we arrived at this. So, it should satisfy obviously those two conditions, velocity 0, V y 0 here, V y equal to V w here. Now, the problem is solved, but we can use check whether the expressions are correct by substituting in the continuity equation. Just as an add on we can do that. So, let us do that. V x was given by a minus b x into h squared minus y squared. So, we will substitute the expression for b, which I have found out now, and then of course, we can also take the expression for v y which I have derived here. Okay, let us substitute in the continuity equation dou v x by dou x plus dou v by dou y, simple differentiation. Okay. Take this v x, differentiate with respect to partially with respect to x, and then take this expression, partial differentiate with respect to y, and in the second term if you take out 3 by h cubed, okay, it becomes very obvious both the terms are equivalent. Of course, the opposite sign, they cancel each other, resulting in 0. Okay. So, that is how you check whether use the continuity equation to, here it is very obvious, we use the continuity equation to get the velocity profile, but just for illustration we are also checking back whether the continuity equation is satisfied. Okay. this porous wall, just if it were just two parallel plates, it would not be interesting. Just because we made it porous, we got a two dimensional field, and so we little more interesting, it became a little more interesting. Okay. That is the selection of problem in a book. The books, when they write, they choose problems or give problems so that they are simple, at the same time put forth the point. For example, in this case, simple modification resulted in a two dimensional flow field. Okay. And good example which combines the integral mass balance and the differential mass balance. Let me first explain the geometry which is shown here. Okay. We have two plates, okay. And thin gap exists between them, okay. And that bottom plate is porous, just like the earlier case, but the top plate is not porous, okay. That is a solid surface. Now, in this case, air enters through the porous plate from the bottom and leaves around the periphery. Okay. Now, if you look at the, so that is the front view, the top view is shown here. So, the flow takes place radially, so you have a plate, air enters and then flows radially out, and that is what is shown as a top view here. Okay. And the front view is of course shown here, the air entering here and then flowing. If you look at the front view, it flows along the radial direction. Now, analysis of this will require cylindrical coordinate system. Once again, we want to restrict to Cartesian coordinate system. What do? I take just two plates, okay, not a circular geometry or anything, just two plates of width W, and then the bottom plate is porous, and analyze the same situation in terms of Cartesian coordinate, and that is what is shown in the right hand side. So, in this case these are plates, okay, and the top plate is not porous, the bottom plate is porous, and gap is very thin, and then we are seeing how flow takes place in the x direction, what is the velocity profile, etc. Okay, let us now read the problem. Air flows into the narrow gap of height h between closely spaced parallel plates through a porous surface as shown. The problem for this figure is shown on the right hand side. Okay. I have also shown the left hand side figure to understand the configuration, the flow, geometry, etc. Use a control volume with outer surface located at position x to show that the uniform velocity in the x direction is V x equal to V naught x by h. What does that mean? Such a profile is shown here. When I say uniform velocity, we have seen this earlier also for application of integral mass balance. Suppose if we have a flow between two parallel plates, when I say uniform velocity, the velocity does not vary in the lateral direction. Okay. Putting it the other way, the velocity does not vary in the direction perpendicular to the flow. Flow is in this direction, perpendicular direction is this. When you say uniform flow, the flow does not vary in the direction perpendicular to the flow. So, such a profile is shown here. We are asked to find out this uniform velocity and in the x direction. In this case, it happens to be a function of x. We will have to prove that, we will have to arrive at this expression. Once we get one velocity component, as we have seen in the previous example, we can get the other velocity component also. So, find expression for the velocity component in the y direction. For the first, we use integral balance to get V x. For the second, we use the differential balance. So, that way this example nicely combines both form of the balance equation. Now, use of integral and differential total mass balance is the object of this example. Okay. So, let us write the integral total mass balance equation. It is a steady state and the velocity is perpendicular to A and the density is uniform across the cross sectional area. Okay. So, this is the integral form of the mass balance equation. There is no transient term and I am writing only the net mass flow term alone. Okay. Now, the control volume is shown here. The question says that the control volume should extend from 0 to a distance x, that is why this control volume is shown here. Now, this control volume has 4 surfaces. Let us split this control surface for those 4 surfaces. What are the 4 surfaces? This is the in surface, okay, and then the porous surface here, and then the surface at x, and then the wall, okay, 4 surfaces. I will call this as in surface, and then this as the porous surface, the bottom one, the right side is the surface at x, the top one is the wall. Now, as we have seen in the previous case, a flow takes place and divides. Similarly, here also flow is along this direction and divides this side and this side. So, along that line there is no velocity, the velocity is 0. So, this first term does not contribute. Once again, it is a x equal to 0 is where flow division takes place, and hence there is no velocity at that particular surface. Now, coming to the bottom surface, it is an inflow surface because flow enters through the porous wall, which is shown by a negative sign. We have seen v dot n is negative for inflow, and then what is the magnitude of velocity is v naught. Of course, I have written rho here. Now, what is the area? Now, we have considered a plate whose width is w, and this distance, the length of the control volume along that direction is x. So, the area is x into w. So, let me repeat again, this term is 0. What we are writing here corresponds to this porous wall, negative because inflow, magnitude of velocity is v naught, we have written density as such, the area is this area up to x and then extending w in the other direction. So, we have x into w as the area. Now, coming to the surface where there is a flow out, a surface at x is outflow, that is why it is positive, density is written as such. What is the magnitude of velocity v x, but now that v x depends on x, that is shown explicitly here. What is the area now? This is the h is the height between the 2 plates, and we have width w, hence the area is h into w. Okay. So, positive indicates outflow, and the magnitude is v x, area is h w. Of course, wall there is no penetration through the wall, hence this term also, this also does not contribute, once again that is 0. So, now let us simplify this. Our objective is to find what is v x. So, v x is v naught into x by h. So, the velocity increases along this direction, Why does it increase? There is flow from this surface. So, whatever flow from the wall that contributes to velocity along the x direction, hence velocity increases along the x direction given by this expression. Okay. So, this is a case where the velocity varies along the flow direction, just like in the last case, okay, and it does not vary in the perpendicular direction. V x is not a function of y, but does not vary in the y direction, but varies only in the x direction, increasing linearly with x. Okay. So, we use the integral total mass balance equation under certain conditions like this and find out what is the x component of velocity and found, which is same as given in the question. So, we have kind of verified. Now, this part is same as what I had done earlier. We know one velocity component, use the continuity equation and then find out the other velocity component. So, this is not something new to this example, but the combination of integral and differential balance is what something new to this example. So, we will start with the differential total mass balance, the continuity equation for steady state incompressible flow, okay, and then write it for the 2 dimensional case, only the first 2 terms are considered. This is exactly what I did in the previous example, no difference at all, but for a different velocity field. So, we will write for dou v y by dou y is equal to minus dou v x by dou x, and then we have seen the velocity profile v x as v naught x by h. We saw the expression as v x is equal to v naught x by h, and then you differentiate that, you get partial with respect to x, we get v naught by h. Now, partial integration with respect to y as we have done earlier. So, v y is minus v naught y by h, once again the constant can be a function of x, and we using the boundary condition we evaluate the constant c. What is the boundary condition? At this location at this surface you have a vertical flow of V naught, we have vertical flow of V naught. So, V y of x is equal to V naught. We also assume this V naught is uniform, this velocity is uniform throughout this length, that is why V y as a function of x is just a constant V naught at y equal to 0, y equal to 0 is this surface, this porous wall. So, when you substitute here y is 0 and V y is V naught. So, see the constant which can be a function of x, here it is just a constant V naught. So, let us substitute back, we get V y equal to V naught into 1 minus y by h, a very simple expression for the vertical component of velocity. When y equal to 0, it is V naught, that is this position, this surface, the bottom surface, and when y equal to h, V naught is 0 because there is no flow through the top surface. So, it satisfies the conditions. So, what is that we have done here is use the integral mass balance equation and got one velocity component, use a differential mass balance, got the other velocity component.